Good morning everyone. So in the last class, recall that we discussed the concept of change of basis, where you have the two bases for the vector space B and for the vector space B, and we are looking for the relation between the coordinates of a vector V with respect to basis B and B dash. Now we are going to discuss the concept of matrices of linear transformation. So where we have a linear transformation T, let's say it is from R2 to R cube, where B is the basis of R2, which is 1 0 and 0 1, and B dash is a basis of R cube, which is as follows. Now let us define a linear transformation. T of xy is x plus y, x minus y, and y. It means that I can write down T of xy as 1 1, 1 minus 1, and 0 1, and xy, and which also means that T of v can expressed as AV if T is a linear transformation, V is where A is a matrix. But at the same time, it's interesting to observe that this is T of V. T of V, so coordinates of T of V with respect to B dash can be written as A times coordinates of vector V with respect to basis P. And in that case, it's again interesting to observe that what is A. But let's see what is happening here. So for example, if I write T of 2 3, then T of 2 3 is 1 1 1 minus 1 0 1 multiplied by 2 3, which is 5 minus 1 3. Now on the left hand side, you can write 5 minus 1 3 as a linear combination of the basis vector of B dash, which is 5 e1 plus minus 1 e2 plus 3 e3, which means that in the case of the standard basis, the coordinates of 5 minus 1 3 with respect to B dash is 5 minus 3 only, and similarly the coordinates of 2 3 with respect to basis B is 2 3, and the columns vector of matrix A are as follows. So if you see the first column, then it should be T of 1 0 and its coordinates with respect to B dash. So what is T of 1 0? So T of 1 0 is 1 1 0. If you substitute here T of 1 0, you will get 1 1 0, which is the first column, and T of 0 1 with respect to B dash is 1 minus 1 and 1, which is the next column of the matrix A. It means that we can always write we can always find the coordinates of T of V with respect to B dash using a matrix A, where A has the columns as T of V1, B dash, T of V2, B dash, and so on. This matrix A is known as the matrix of linear transformation. So let us consider V and W be the two vector spaces with dimension n and m. B and B dash are their bases. Here we are talking of the ordered basis because we are talking of the coordinates. When you write 2 3 as a linear combination of 2 1 0 plus 3 0 1, so here coordinates are 2 3. You cannot write it as 2 times 0 1 plus 3 times 1 0. So this is not allowed. And T is a linear transformation, then a matrix A, which is denoted as T of V1 B dash, T of V2 B dash, and so on. So T of V1 B dash represents the first column of matrix A. So then there exists a unique matrix satisfying this condition. T of V B dash is equal to A times V of P. and this matrix A is known as the matrix for T relative to basis B and B dash, and this is how it is denoted. Yes, so here the idea is that if we have the coordinates of vector V with respect to basis B, and if we have matrix A, then we can always compute the coordinates of T of V with respect to basis B dash. And if U is equal to V, in that case we will assume B is equal to B dash if they are not given separately, and if B is equal to B dash, then of course the matrix for T related to basis B is denoted as TB, which is T of V1, B and so on, and this is a special case where T of VB is equal to T of B, V of B. Okay, so please do really remember the formulas, then the questions are quite easy to follow. So first one says that compute T B dash B where B and B dash are given. So recall that how do you compute this? So the first column is T of V1, V1 is already given with respect to B dash, and T of V2 with respect to B dash. So V1, V2, V3 they represents the basis vectors of B. So now first I should compute T of V1, which means T of X. So it is given that T of Px is xpx. So T of X is x square and T of 1 is x. Now I should express x square as a linear combination of the vectors of B dash that gives me the coordinates of T of X with respect to basis B dash. In this case a lot of computation is not required, straightforward, because I can write x square as x square plus 0x minus 1 plus 0x plus 1, and similarly I can write x as 0x square plus half x minus 1 plus half x plus 1. It means that the required matrix is, the first column is, here it's 1, so 1 0 0, coordinates of x square with respect to basis B dash are 1 0 0, and coordinates of x with respect to basis B dash is 0 half and half. So this is my required matrix. All the solutions have been added to the slides also. Let's quickly see the other question. Here V and W, the vector spaces, are same and therefore only one base is given. First I have to compute T of B, and using T of B I must compute T of 3 plus 2x minus x square. Please do try by yourself. So T of V, to compute T of V I must compute T of V1, T of V2 and T of V3. So T of 1, so P of x becomes P of 2x minus 1. So a function of x becomes a function of 2x minus 1. So 1 is constant, remains 1. T of x becomes 2x minus 1, and T of x square becomes 2x minus 1 whole square, which is 4x square minus 4x plus 1. So now I have to see the coordinates of T of 1, T of x and T of x square with respect to standard basis 1x and x square, which is straightforward. So here the coordinates are 1 0 0, because 1 plus 0x plus 0x square. Here it is minus 1 2 and 0, because we are considering the ordered basis, and here is 1 minus 4 and 4. So my required matrix is 1 0 0 minus 1 2 0 1 minus 4 4. And now T of 3 plus 2x minus x square is 1 0 0 minus 1 2 0 1 minus 1 4 multiplied by V of B. So V is 3 plus 2x minus x square. Its coordinate with respect to basis B are 3 2 minus 1, and if you multiply it, then it gives you 0, 3 minus 2 minus 1, then 8 and minus 4. It means that this gives you the coordinates with respect to basis B, and what you are looking for, you are looking for the vector. So t of 3 plus 2x minus x square is 0 plus 8x minus 4x square. Okay, now this method I have already discussed in the section change of basis. I am not going to the detail that how this method has come, but this helps us to reduce the computation. It says that if we have B and B dash as the basis for Rn and Rn, or for the vector space V and W, and T be a linear transformation, then to compute T of B dash B, I must compute T of Vi first, which we are doing, and then I can write W1 as the first column, W2 as the second column, and so on, and then T of V1 as the first column, second column, and then I compute its RREF. While computing RREF, the left side becomes the identity matrix and the right hand side gives us the required matrix. If you recall the section change of basis, then this method is very much familiar and very easy to use. Let's see some questions based on this method. So it says that basis B is given because V is equal to W, and we need to compute T P. So the first step is to compute T of V1, T of V2, which means I must compute T of 1 minus 1 and T of 0, 1. After computing it, we will use the previous method. So T of 1 minus 1 comes out to be 2, 0, and this comes out to be minus 1, 1. Then the method says that I must write W1. So here U1, W1 both are the basis vector because basis is fixed B. So this is 1 minus 1, the first column, then 0, 1, then T of V1 which is 2, 0, then T of V2 which is minus 1, 1. And then I must compute its RREF. If you compute it, do it by yourself, you will get 1, 0, 0, 1, 2, minus 1, 2, 0. And this means that my required matrix TB is 2, minus 1, 2, 0. Okay, again the solution is here. Let's quickly try one more question. Here B and B dash are given and I have to compute T B dash B. To compute T B dash B, I first need T of V1, T of V2. So T of AB is given. So T of V1 is T of 5, 3 and T of 3, 2. If you substitute the values here, you will get 10x square plus 5x plus 12x plus 6, and this is 7x square plus 7x plus 4. Yes, it means that W1, W2 are already given. So W1, this is W1, so this is 3 minus 2, 0, then W2 minus 2, 2 minus 1, then 1 minus 1, 1, and then 10, 12, 6, 7, 7, 4. And now I must compute its RREF. So after computing RREF, it gives me 1, 0, 0, 0, 0, 1, and this is 22, 62, 68, 14, 39, 43. Please verify the calculation by yourself, and therefore this is my required matrix. There are few exercises also which I have added. You can try them by yourself. And then let's move to a very interesting question. I suggest you to spend some time in thinking over it and try to do it by yourself first. It says that T is a linear transformation from P1 to P1 with respect to basis B. Then I have to find the matrix of T with respect to basis C. Now first thing to understand that what is given and what need to be found. To find the matrix of T, which means T of C with so to find T of C, the first requirement is I must know what is T of X and what is T of 1, which is not given because the linear transformation is not given. If I have T of X and T of 1, then I have to see their coordinates with respect to the basis C. Now what is given? So I have given the matrix TB, which is 2 minus 1 3 minus 2. Now recall that the first column is T of V1 with respect to B, because here B is equal to B dash, and T of V2 with respect to B. So here the coordinates are given and the basis vectors are given. For example, if the coordinates are 2 and 3 and the basis vector are 4 5 and 1 2, then 2 multiplied by 4 5 plus 3 multiplied by 1 2 gives me the required vector whose coordinates are given. So it means that once I have given the coordinates and I have the basis B, I can compute T of V1. So T of V1 is 2 times, this is first column, so 2 times x plus 1 minus 1 x minus 1, and T of V2 is 3 times x plus 1 minus 2 x minus 1. Yes, so now I have T of x plus 1 and T of x minus 1. So this is now T of x plus 1 can be written as T of x plus T of 1, because T is a linear transformation, which is x plus 3, and T of x minus 1 can be written as T of x minus T of 1. If I add them, then adding them gives me T of x is 2x plus 8 by 2, which is x plus 4. If I subtract them, then T of 1 becomes minus 2 by 2, which is minus 1. It means that with respect to basis C, the coordinates of T of x and T of 1 can easily be seen. So it is 1 comma 4. So now T of C, so the first columns are coordinates of T of x with respect to basis C, so which is 1 dot x plus 1 plus 4 dot 1, so which is 1 4, and next one is 0 minus 1, which is my required matrix. So very interesting question. The next question says that if B and B dash are basis of R2 and T is a linear transformation where T B dash B are given, compute T of 5 comma 5. Again, the only thing is the linear transformation T is not given, but the matrix is given. So as we did in the previous question, we must compute the linear transformation. So T of B dash B is given, which is 4 2 3 minus 4, which is T of V1. Even if you write V1 as 1 2, so T of 1 2 and with respect to B dash, and T of 2 minus 1 with respect to B dash are given. It means T of 1 2 is 4 times the first basis vector of B dash, which is 1 0, and 2 times 0 1, which becomes 4 2, and T of 2 comma minus 1 is 3 times 1 0 and minus 4 times, this is the second column, 3 minus 4 0 1, that gives me 3 minus 4. Now I need 5 5. So first I have to write, because I have T of 1 2 and T of 2 minus 1, I must write 5 5 as a linear combination of 1 2 and 2 minus 1, and then I must apply t on both the sides. So either you can write it as a times 1 2 plus b times 2 minus 1, solve the homogeneous system of equation, or you can see that it is simply 3 times 1 2 plus 2 minus 1, and if you apply t on both the sides, then this is t of 3 1 2 plus 2 minus 1. Now recall that t is a linear transformation, therefore it can be written as 3 times t of 1 2 plus t of 2 minus 1. T of 1 2 has already been computed, so 3 times 4 2 plus 3 minus 4, so 12 plus 3 15, and 3 to just 6 minus 4, which is 2, so 15 2 is the required answer. Okay, this is again interesting exercise, please do try by yourself. And then a quick result, it says that if you have t1 t2 as two linear transformation, we already know that t2 of t1 is t2 multiplied by t1, and therefore their coordinates, so we are using the same concept, so t2 of t1 with respect to b dash b is t2 of b dash b double dash and t1 of b double dash b. Easy observation, and based on this observation there is a question, so try it by yourself. Try to compute t2 of b dash b double dash, t1 of b double dash b, then you multiply these two matrices to have t2 of t1 b dash b, and then t2 of t1 means you use this coordinates to compute t2 of t1 with respect to a vector v. So these are the required matrices, and now t2 of t1 is defined from p1 to p2, therefore you must try to compute t2 of t1 v, where v is a vector belonging to p1. Now t2 of t1 v with respect to b dash is, you have this matrix and multiplied by the coordinates of v with respect to the given basis. So this is standard basis which is given, I think 1x must be given as the standard basis, yeah, so 1x is given as b, and therefore t2 of t1 v b dash becomes 0 6a minus 9b and 0. If you need t2 of t1 v, then you simply multiply it with this standard basis, which is 1x x square x cube, and that's why you get 6ax minus 9b x square, which is the required answer. And one last quick result, if t is 1 1, then t of b is invertible, and this is how it is defined. I am not going into the much detail here, but this complete this module. So there remains the last module which we are going to discuss in the next class, which is eigenvalue and eigenvector. Thank you very much for watching the video.